right. Can anyone hear me? Perfect. Welcome to United Astronomy Clubs of New Jersey. So while I'm waiting for last few people to kind of come down and get settled in, I want to welcome you guys once again to our site in Jenny Jump State Forest in Hope, New Jersey. Uh, we are live streaming on YouTube and Twitch, so uh, I will be monitoring that through various electronic devices tonight. While everyone's getting settled in, do check us out on our website, uacnj.org. That's where you're going to find a list of all our upcoming and past talks, as well as information on our member clubs and a little bit about our mission, which is to bring astronomy and science to as many people as we can. You can also check us out on our social media, so Facebook, Instagram, the social media site formerly known as Twitter. You know, all of the above. We have the Discord channel for people who want to ask questions, share their astrophotography photos and whatnot. So do check us out on there. Hit those like and subscribe, like I said, on Twitch and YouTube. It does help us to know that we are doing well. Now, for the people who are here, a little safety briefing. If you need to use the bathroom, that is the porta potty in the back to my left, your right. I also have a little museum and gift shop area that I'll be manning after the stream. Unfortunately, they still have not given me the ability to be in two places at once. Once I do that, I will conquer the world. It'll be so nice. Besides that, each of the sheds you see over there is an observatory with the roll-off roof and houses its own telescope. After the presentation, you'll be able to ask questions of the volunteer running it, see what they're seeing through the telescope. I think I see Paul over there set up for electronically assisted astronomy, which is where you guys get to view it on a screen. But that's not what we're here right now for. Right now, we're here for the talk about James Webb Space Telescope, the 20-month update. Walt Windish here will be presenting that, and Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1985, well before I was ever alive, just in time to see Halley's Comet. Walt is a member of the North Jersey Astronomical Group and the Rockland Astronomy Club. He's been volunteering here at Jenny Jump for over 20 years, and he's going to tell us all about that telescope in the sky.
Thank you. Thanks a lot. Thanks for braving it out here when my name is on the schedule. Usually I bring thunderstorms with me. Matter of fact, I was the first to beta test our thunderstorm and lightning contingency plan for speakers. So it looks like one of the nicest nights I've seen in quite a while. So I think we'll get some good stargazing in as well. But
don't jinx it, Walt.
Yeah, I know. I'm going to just jinx myself, and in come the black clouds. But tonight I want to spend some time talking about the James Webb Space Telescope and look at some of the advances. You know, if you look at the press releases in one year, I call this a 20-month update, but we've only been receiving images from James Webb since July of last year. And in 1 year, it's amazing all the stuff that it's imaged and the discoveries and how some of what we thought we knew, we realized we don't know. Very exciting stuff. And I really hope when I do these talks that people will get interested enough to go and just Google some stuff yourself. Everything I show you, you can find on the web. You can get it NASA, JPL, European Space Agency. You can find all this stuff on the web and go a lot deeper if you're interested in any of the topics. So the James Webb Telescope was launched Christmas Day 2021 around 7 a.m. It cost us $10 billion, and it's a joint project between NASA, the European Space Agency, and the Canadian Space Agency. And the first 5 images from this telescope were released on July 12th of 2022. So we really have only been receiving images for about 13 months. We'll spend most of our time looking at what we've done with the telescope so far. And I say what we've done because if you pay taxes, you are our financial partner in this project. And that's why much of what NASA releases just goes out into the public domain because we've already paid for it. So there's a picture of the Webb telescope. So the James Webb telescope is very different than the Hubble telescope. The Hubble telescope still looks like what we think a telescope should look like. A tube, right? This one, of course, floating in space. The tube of the Hubble protects the primary mirror from the glare of the sun and all the space junk that's floating around up there. The Webb, as you can see, is just out there. There's no tube protecting its primary and very expensive mirror. It uses a complex sun shield to shield it from the sun, and the sun shield is 22 meters by 12 meters. That's about the size of a tennis court. So flying out there and then unraveling this telescope was quite a big deal. I mean, the mirror folded out, the sun shield folded out. There were many failure points that could have trashed this project before it even started. The mission duration is planned for about 5 to 10 years. But if it's built as well as the other telescopes we've put up there, it should last quite a bit longer. For any astro nerds out there, the Webb's primary meter is 25 square meters. It's broken into 18 segments. And Jeff Williams, one of our members, just 3D printed a replica of the James Webb primary mirror. It's not parabolic though, like the James Webb is. You'll have to work on that next time. So as big as this mirror is, the gold coating on it weighs only 48 grams, which is less than 2 ounces. So less than 2 ounces of gold coats 25 square meters. That in itself is pretty amazing. The JWST mirror has 6.25 the light collecting area as the Hubble. The Hubble was about 4.5 square meters, and you could see the difference in scale. Person, Hubble's primary mirror, and the Webb primary mirror. That's quite an advance. Astronomers will tell you it's the light gathering power of a telescope more than the magnification that counts. So if you go to one of those department stores and you see these little department store telescopes and they say, 900x magnification, well, it only gathers but this much light, and it's not going to do much for you. You're not going to see any detail to it. What you need is a big light bucket. Here's another huge difference. The Hubble orbits the Earth at about 355 miles. That was close enough to fly it up with a space shuttle and even send astronauts up there to do maintenance. And if anybody remembers, very embarrassing for NASA, but when they sent the Hubble up there, there was a defect in the mirror they didn't catch, and they had to send an astronaut up there to fix it from the get-go. So we had a defective telescope up there. The Webb sits at a really cool spot known as a Lagrange point. It's just under 1 million miles from Earth, so quite a difference in distance. About 1/100th of the way to the sun. It had to be launched by a rocket and had a long way to travel. Between the long voyage and the much more complex deployment that was required, it took about 5 months to get it set up, tested, and ready to go. That's why it launched in December, and we didn't see pictures till about July. And by the way, we are not going to be sending astronauts up to the Lagrange point 1 million miles away. That's not happening unless we have some breakthrough in space travel. So simply put, a Lagrange point is a special spot in space where the gravitational forces of a two-body system and the orbital motion of the body balance each other out. It's a nice parking space. You can almost, it's not the same principle, but you can almost think of an eddy on a stream where the water's flowing and then there's this one area where objects can stay put. That's where we've parked it. There's 5 Lagrange spots in every star and planet system. And as you can see, 3 of them are in a row. L3 is on the other side of the sun. L2 is between Earth and the sun. L1. L2 is where the Webb scope is parked, and it actually revolves around the point. It doesn't sit in the point. Now, of course, one of the dangers of putting it in a Lagrange point is that other objects can sit there too. And we've already had a micrometeorite strike on the mirror, a very tiny speck of dust. Worried some people, but the mirror is fine. It's marked, but it's fine and it's operational. So my guess is if anything shortens the life of this, it might be something striking it at that Lagrange point. But it's far enough from the space junk floating around us, and more importantly, it allows us to use that huge solar shield on the Webb, which is critical because this is an infrared telescope. Unlike the Hubble, this sees well, Hubble saw an infrared too, but it was mostly visible. This is all infrared, and infrared works on detecting heat at long, long distances, so we've got to shield it from the sun. Let's take a real quick science break and talk about the electromagnetic spectrum. We only see a small portion of the spectrum known as visible light. And you can see that right there. The Hubble Space Telescope is parked right off of it because it was mainly a visible light instrument, although it did a lot of work in ultraviolet and some work in infrared. Our eyes are like a camera with a shutter speed of 1/30th of a second. So even though we can look at something in the sky through a telescope and see the object, we won't be able to see color, like those beautiful photographs that we see in astronomy books, because our eye just doesn't gather enough light. You have to have a long exposure, and our eye's not capable of that. So when you look up and you see even a beautiful object, it will look like a fuzzy kind of a cloud. It'll look like a cloud floating there. You'll see it in black and white. And one trick, if you're looking through the scope tonight, and if you are looking at something like the Ring Nebula or something, look to the side of it. The side of your eye is more sensitive to light than the middle of your eye. So if you're looking directly at an object, you're not going to see as much as if you trained your eye. That's called averted vision. If you train yourself to look to the side of the object, you'll see that object grow in size just because you're using the part of your eye that's more sensitive to light. So outside the visible spectrum, we have infrared, microwave, radio, and lower frequencies. Ultraviolet, all the way up to gamma rays, which is the highest frequency and highest energy part of the spectrum. So as I said, the Hubble specialized in visible light, but also ultraviolet and some infrared. As you can see in the slide, we've got space-based and ground-level instruments that cover pretty much the whole spectrum. And by putting the information that we get from these instruments together, we can gather a lot more than any single instrument by itself can tell us. The James Webb will operate mostly in the near infrared. And infrared allows astronomers to cut through a lot of the dust and the clouds that encircle the objects that we're interested in. And we can see details that are unreachable in the visible light spectrum. So let's take a quick look to see what that means. The top here, this is a side-by-side comparison of a Hubble image on top with a James Webb image on the bottom. And this is a stretch we call the cosmic cliffs on the Carina Nebula. And here we can not only see an increase in the resolving power down below when you look at the structures of these clouds, but we also see how it cuts through those dust clouds and give us a more detailed look at the stars behind it. It's quite dramatic between Hubble's visible light view and the Webb's near-infrared light view. And by the way, scientists have to colorize anything that's not taken in visible light. So when they get the infrared data from the James Webb, they've got to color it so we can see it. It doesn't come out like a Polaroid camera. These are two deep field images of the same region of space. A deep field image is simply you point it where the sky looks like it's empty and you see what's way, way out there, 5 billion light years plus away from us. So the Hubble image is on the left, and the Webb image is on the right. The redder an object is, the further away that object is. And of course, the further away the object is, the farther back in time we are looking. Because we can think of a telescope as a time machine. If you see a galaxy, and there are galaxies in this picture that are 5 and 10 billion light years away. If you see something that's 5 billion light years away, you're seeing light that's 5 billion years old. It took that light 5 billion years to get here. So we're not actually seeing how that galaxy looks today. We're seeing how that galaxy looked 5 billion years ago. And it's pretty cool to think of that when you're looking up in the sky at objects that are that far, especially when you're looking at distant galaxies. And you can look at distant galaxies right here. So the Hubble provided many of the ideas that we use for our Webb missions. And the Hubble showed us our ignorance in some case. And I think the Webb's really going to show us our ignorance to the second power. You know, a truly wise person is not wise, doesn't get wiser in their own eyes. They get less wise. And the reason for that is because if you learn something and you know something well, you realize there's 10 other things that you know nothing about. And so you're feeling a little dumber and not a little smarter all the time. That's the paradox. NASA administrator Bill Nelson may have been thinking about that when he said, "The promise of Webb is not what we know we will discover. It's what we don't yet understand or can't yet fathom about our universe. I can't wait to see what it uncovers." There's a lot of wisdom in that. He realizes that we're going to uncover stuff that we had no idea we were going to uncover. Just because every time the technology increases, we can see deeper into space and we can see it in better detail. And therefore, the better the data, the more we have to work with as far as developing our knowledge about the universe. So back in July 22, just as soon as the Webb itself got itself unfolded, it went right to work and discovered what was thought to be the oldest galaxy known to science, oldest by about 100 million years old. It was initially named Glass Z13, and glass comes from the catalog. When scientists do surveys, they usually name the catalog that they're surveying, and this was the glass survey. And Z13 denotes redshift, how fast the object was moving from us, which means how far it was. And so that was a JPL survey. This galaxy is about 300 million years after the Big Bang. So we say the universe is about 13.7, 13.8 billion years old. This was about 13.3 billion light years away. And I know that picture isn't all that impressive, but think of how you'd look if you were traveling for that many billion years. At the same time, scientists found another galaxy, and they named it Glass Z11. So Z11 means the redshift was 11, so it's not as far as Z13. And that was about the same age as the previous record holder, which was GN Z11. Both of these new galaxies, Z11 and 13, are kind of small. One is 1,600 light years across, the other's 2,300 light years across. So compare that to our galaxy, which is 100,000 light years across, or the Andromeda galaxy, which is about 220,000 light years across. But these galaxies, Z11 and Z13, were discovered in a early release of data that was not publicly released on the July 12th date. It was held back a little bit till they took a good look at it. And then later, scientists determined that the redshift of Glass Z13 was not quite Z13. They renamed it Z12. And this galaxy, HD1, which was discovered by the Earth-based telescope, the Subaru, took the place of the furthest galaxy that we know. It had Z of 13.27. Pretty competitive stuff. But glass Z12 found by the Webb telescope, is still an impressive find. But it goes to show you that scientists always need to be ready to subject their findings to new data and peer review. The data is still being peer reviewed, even now. And it may turn out that one of the other Webb galaxies is older. Webb has found about 40 ancient galaxies so far. But the important thing to understand is that it's always being peer reviewed. You know, sometimes you see people on social media saying, you know, trust the science, as if when science says something, it's a closed book. Well, a good scientist doesn't think like that. He's always looking to test his hypotheses or her hypotheses and see if the data still supports what that hypothesis says. Now, of course, if you're talking to someone who thinks the Earth is flat, you might want to tell them to trust the science. That's pretty much a settled case. And I know they're out there on social media, but I'm not talking about those people. I wouldn't even answer those people. So this is a really cool galaxy. It's known as M74, or the Phantom Galaxy. It's called the Phantom Galaxy because amateur astronomers have a hard time finding it. It's a very dim galaxy. It's hard to see. And it's a great example of how different observatories working together at different wavelengths can provide a much clearer picture of an object than any one of those observatories by themselves. The European Space Agency notes about this galaxy, such a variety of galactic features is rare to see in a single image. And this image is a combination of Hubble in the visible and Webb in the near infrared. And that's a composite of those two observations. The red colors mark dust that's threaded through the arms of the galaxy. Lighter oranges show hotter dust. The young stars throughout the arms and nuclear core are shown in blue. And pretty much if you're looking at a picture of a galaxy and you see some really heavy-duty blue going through, you know those are hot young stars that are going to burn out quickly, but they're very hot. Heavy older stars are towards the galaxy's center and are shown in cyan and green. And then bubbles of star formation, protostars coming into life, are also visible in pink across the arms. So you have a lot of dust in these galaxies. And when there's enough gravity, when there's enough mass, they start to compress and get hotter and hotter. And then we have nuclear fusion, and we have a star blinking into existence. And then you have the gravity is pulling in, and the nuclear explosions are pulling out. And finally, after about 100 million years, these stars will reach what's called hydrostatic equilibrium and spend their life at that size until they run out of hydrogen to burn. And then they do all kinds of crazy things. And if they're big enough, they'll go supernova on you. I like this image because it gives you a good idea of the two images that went through it. The Hubble image is on the left, invisible, and the Webb image in infrared is on the right, and the image we just looked at is in the center. Notice the amazing clarity of that Webb image on the right. This picture was just released in August of 2022. This galaxy is one of 19 nearby star-forming galaxies to be charted and studied by the Webb team. The candidates were originally selected from Hubble and land-based telescopes. And the European Space Agency noted on their website that the addition of crystal clear Webb observations at longer wavelengths will allow astronomers to pinpoint star-forming regions in the galaxies, accurately measure the masses and ages of star clusters, and gain insights into the nature of the small grains of dust drifting in interstellar space. And here's the Webb shot by itself. I just love that image. The blue eye in the middle looks a little sinister to me, though, but the amount of detail is just amazing. Here's another side by side. On the left, we've got the Hubble image of Uranus taken in 2022. And on the right, it was Webb taken in 2023. And yes, NASA aimed their space telescope at Uranus. Let's get that out of the way. We're done. Be done with that. But look at all the extra detail we say in the Webb photos of the ring. Just amazing. This Webb photo gives us amazing detail of 11 of the 13 icy rings around Uranus. Only the Voyager 2 spacecraft in 1986 and the Earth-based Keck Observatory with its fancy adaptive optics have imaged the faintest rings. And this again is another color representative image. Also notice it gives us a nice view. It's kind of hard to see probably from there, but there's a nice view of a polar cap. It takes Uranus 82 years to orbit the sun, so each hemisphere of Uranus experiences a winter lasting about 20.5 years. Not a pretty picture. And NASA noted that on the right side of the planet there's an area of brightening of the pole facing the sun known as the polar cap. The polar cap is unique to Uranus. It seems to appear when the pole enters direct sunlight in the summer and vanishes in the fall. And this Webb data will help scientists understand the nature of this. And Webb revealed also a surprising aspect of the polar cap. There's a subtle enhanced brightening at the center of the cap. And nobody knows what that is yet, but they are studying it. But the sensitivity and longer wavelength of Webb's NRC cam may be why we can see this enhanced polar feature when it has not been seen clearly with any other telescope. The Webb scope also took this great wide-angle view of Uranus. 6 of its known 27 moons are annotated. You can see their name there. I know it's kind of hard from the back, but this is the whole system of Uranus, at least 6 out of the 27. And it's a single 12-minute exposure, which is pretty remarkable. Many times there's multiple exposures that are stacked on top of each other, or there's accumulation of hours of light. But it is in our solar system, so it's a little closer, it's a little brighter, but just one 12-minute exposure was all they needed to map this system. So here's a photo taken by Voyager 2 in 1986. Back then, the spacecraft was responsible for the discovery of 2 rings, bringing it to a total of 12. Then in the early 2000s, Hubble took this series of images, and it was unable to see the 2 fainter outer rings that the Voyager discovered, although the Keck scope could. The Keck scope in Hawaii is a pretty amazing ground-based scope. It sends up this laser beam to look at the atmosphere, and it's able to adjust its mirrors and align its mirrors to compensate for the atmosphere. It's just amazing. The Subaru scope. And by the way, Subaru is Japanese for the Pleiades, and the Pleiades is a star cluster that we see in the sky. That's why when you look at a Subaru car, you see the stars on it. It's because it's a star cluster that Subaru is named after. Oh, notice that these photos of Uranus show the rings horizontally. When other planets' rings are horizontal, right? They're close to the plane that they revolve around the sun, but these are at 100 degrees. The rings of Uranus are 100 degrees off that plane. It's a very weird tilt. The leading theory of why it's tilted like that is that probably an object the size of Earth crashed into it and knocked it on its side. But again, that's forensic astronomy. This orientation means that the planet's poles experience many years of constant sunlight followed by an equal number of years of constant darkness. So here's a fun fact for you. Jupiter, Saturn, Uranus, and Neptune all have rings. We've known about Saturn's rings since the 17th century when Galileo discovered them in his small 20-power telescope. Although he thought they were handles or really big moons on both sides of Saturn. He didn't have the resolving power to actually see that they were rings. He just saw these 2 blurbs on both sides of Saturn. By the way, Saturn is going to be the brightest in a long time, from August 17th to September something. So this is the time to see Saturn. It's really going to brighten up, and you'll get some good views of that. And to see the rings of Saturn for the first time is just breathtaking. But it wasn't until 1970s or later that the rings around the other gas giants were discovered, and they're closer. The rings around Uranus were discovered in 1977 using the Kuiper Airborne Observatory, and the astronomers were actually looking for it to occult a star so they can find out more about the atmosphere. And they saw a dimming of the light earlier than they expected and realized that those were rings. So that was in 1977. Jupiter's rings were discovered in 1979 during the Voyager 1 flyby, and the rings around Neptune weren't discovered until 1989 when Voyager 2 flew by. So we had to fly spacecraft by two of the planets to discover these rings, because they're very faint and they're little chunks of ice and rock. And speaking of planets, let's take another look at Webb's major achievement, the first direct image of an exoplanet. One of the major goals of the Webb Space Telescope is to discover exoplanets. And exoplanets merely mean that it's a planet that exists outside of the solar system. So an exoplanet is not in our system. And astronomers have found thousands of exoplanets since the first were discovered in 1992. Most were too far away or too close to the sun to directly image. But in September 2022, NASA released these 4 images on the bottom. They're direct images of an exoplanet orbiting a star known as HIP 65426. The European Southern Observatory in the southern hemisphere, because the constellation Centaurus, which it was found in, can only be seen in the southern hemisphere, discovered this super Jupiter-sized planet orbiting the star in 2017 and designated it with the same number as the star, but put a little b at the end. The system's about 385 light years away from us. But what's really exciting is it's the first time that we actually got a direct image of an exoplanet, and 4 images at that. The image of the exoplanet is seen here through 4 different light filters, and it shows how Webb's powerful infrared instruments can capture worlds beyond our solar system. The 2 images on the left were taken with the NIRC cam, NARCam, near infrared camera, which is the near infrared camera. The 2 images on the right were taken with the MIRI, which is a mid-infrared instrument. So it's a little longer wavelength than the NIRCam. The picture shows where the star is. You can see this is the planet. And these are just part of the optics. These are not objects. Just this. These are aberrations. But this is where the star is in all of these. So it's quite a distance. They blotted the star out with an instrument known as a coronagraph, because if they didn't blot the star out, it would be so bright we wouldn't be able to see this planet. So they have a special instrument that can blot it out. And again, the bars on the left 2 images are just artifacts of the telescope's optics. They're not actual objects. The huge planet is orbiting its sun at about 100 times the distance of Earth from the sun, which is over 9 billion miles. It's 3 times the distance that Pluto, 3 times the distance that Pluto orbits the sun. And that might be the reason why this is the first exoplanet we were successful at imaging, because it's so far away and it's so big. It's about 6 or 7 times the size of Jupiter, which is our largest planet. So this is a huge planet far away from its sun, and we were able to capture it on our instruments. 385 light years away. So that's light from 385 years ago. So the real teaser in this shot is that it's pointing the way to future observations. And who knows what we can do in exoplanet work. And since it's one of the priorities of the instrument, I think we can be sure to see some interesting stuff coming out of these observations. So one concept that's important to understand before we go a little further is redshift. And I've already mentioned redshift, how the number after Z talks about the redshift. It's also called Doppler shift. And if you're standing still and a race car goes by you, you hear the pitch seems to increase as it comes towards you, and as it goes away, you hear it goes, right? You hear the pitch go down in frequency, right? And the reason for that is that the sound waves, as it's coming towards you, are being compressed into shorter wavelengths, which makes the pitch higher. And after it passes you, the wavelengths are being stretched out. The wavelengths are getting longer, and that's why we can hear the sound getting lower. Well, the same thing happens with light. If an object's moving towards you, its light is going to be shifted towards the blue. And if it's moving away from you, it's going to be shifted towards the red, which is the lower frequency part of the spectrum. And the faster it's moving, the more it's going to be shifted to the blue towards you or to the red going away from you. Everything in this universe is moving away from each other, except for a couple of local objects, a couple stars nearby us, and the Andromeda Galaxy. The Andromeda Galaxy is blue shifted. It'll crash into our Milky Way galaxy in about 4 billion years. But not to worry, I think the sun will come close to toasting us by then. So 4 billion years one way or the other. And actually, when galaxies come together, it looks like it's a catastrophic collision, but there's so much space in between stars that they really don't. They form a lot of new stars because the gas gets compressed, but it's not like everything's crashing into each other. And you can see some pictures of galaxies colliding. It's pretty cool stuff. But yeah, Andromeda Galaxy is moving towards us at about 250,000 miles per hour. So I guess when they come together, we can call it the Milkometa or something like that. I don't know what they're going to call them. I won't have to worry about that. But redshift is used to find exoplanets, as we discussed. And I'm not gonna spend a lot of time on this. This method is called radial velocity. It's the second most productive way of discovering exoplanets. And earthsky.org notes that astronomers have learned to tease out a subtle tug of a distant planet on its parent star, thus revealing the planet to astronomers. This is like just the slightest. It's amazing they can even measure it. The slightest bit of wobble will show them that there's some kind of gravitational tug on it, because obviously planets, even a huge one 6 times the size of Jupiter, is still, you could fit 1,000 Jupiters inside of the sun. So it's really a small, and that's our largest. So we're talking about just a slight gravitational wobble. So the astronomers can infer that the star is alternating between moving towards and away from us just by looking at a red shift turning to a blue shift, and just that slight wobble that they can actually measure. Something must be pulling on the star if that's the case. And by measuring how far the absorption lights, what they do is they look at the absorption lines on different elements, and they shift to the red or shift to the blue. They can determine the mass of the invisible companion and its distance from the star, and come to the conclusion that a planet is in orbit around the star. This method recognizes the fact that if a star has a planet or planets around it, it's not strictly the planets orbiting around the sun. It's the sun and the planets are orbiting around a center of gravity, a common center of mass. And because the star is so much more massive than the planets, that center of mass is usually inside the star, but it's not in the middle of the star. It's skewed to the side depending on the amount of mass that's orbiting it. And that's how you get the wobble, because it is rotating around that center, even though the center's in it. And by doing that, you can picture how that's wobbling. And when it goes away from the observer, there's a red shift. When it comes towards the observer, there's a blue shift. And we now have instruments that can actually measure that. Before we ever used redshift to measure the wobble of a sun to discover exoplanets, we used redshift to discover the movement of galaxies, how far away they are, just as we were talking before about galaxies Z13, Z12, Z11. Those are the redshifts, and they are at the far edge of our universe. And we measured the redshift, and that tells us how far away it is. It tells us a lot of things about the star. And this fits right into another one of James Webb's priorities, and that is to look at data that will give us an idea of how this universe came into being and give us more information about the universe. I mean, the universe is expanding. And the expansion of the universe has been controversial one way or another since Einstein wrote his theory of relativity. Einstein's equations showed that the universe would be expanding. And he didn't like that, because if you play the film backwards, it means that the universe had a beginning. And he put a cosmological constant in there to keep the universe at a steady state. And that was, mathematicians called him out on it over time. And later on, he described that as one of his biggest fumbles that he made in his career, was putting that constant in there. And it was not because the science told him that, it was because of his philosophical presuppositions that were in there. But now the controversy is how fast, and is the universe expansion increasing, and how fast is it increasing, and what does that mean? There's all kinds of questions that still need to be solved regarding the expansion of this universe, and we're hoping that we can get better and better measurements using the Webb data and figure some of this stuff out a little more. So this slide is basically illustrates two current theories of formation of the universes. The top one is a standard model of Big Bang that scientists have been using for years, where the Big Bang, after the Big Bang, the universe was a hot soup for a couple thousand years. Then it started to reionize, and finally stars and then galaxies started to appear. The newer theory is that in the phase we think of as reionization, the first black holes formed, followed by the first stars and then modern galaxies. The first stars are known as population 3 stars, and they exist only in theory because none have been observed, because they'd be too faint, right? The first stars that were created in the universe. Since there were no stars around to create heavier elements, we think population 3 stars were formed out of pure hydrogen and helium. Right? As more and more stars lived their lives, and some big stars, the biggest stars, some of them only live for about 100 million years, and they make all kinds of heavy metals inside them. And so when it goes supernova, those metals are dispersed into the universe. And so older stars now have those metals incorporated into them. And we can tell that by looking at the spectrum. Each element has a specific spectrum, absorption lines that are spaced evenly. Even if they're redshifted, the spacing of those lines are such that scientists can tell, okay, that's carbon, that's iron, and so they can tell what the different elements are. And so the theory is the first stars that were formed purely out of hydrogen and helium. The formation of these heavier elements is known as nucleosynthesis. And just to give you a little intellectual constipation, there is a star out there called Methuselah, and I'm not going to get into it right now. I talked about it last time I was up here. It may be one of those prototypical stars, maybe one of those population 3 stars. It lacks heavy metals, and the weird thing is our best calculations measure its life to be older than the universe. So is that a calculation error? Is it an error in the way we've aged the universe? We don't know. But that Methuselah star, it's worth reading up on if you're interested in that kind of stuff. Let's see how I'm doing on time. All right. So here's a composite image of the Southern Ring Nebula with the Hubble image on the left and the Webb image on the right. And it's easy to see the extra detail that we're getting from the Webb telescope. This is because its mirror is about 3 times larger than the Hubble's. These are 2 full pictures of the Southern Ring Nebula side by side, and both of them were taken with the Webb, so they've got some high resolution. The one on the left was taken with the near infrared cam. The one on the right was taken with the mid-infrared cam. So you can see we're getting different details, we're getting different data, we're getting a different picture of the same object, and it's telling us different stuff about it. So the one on the left, the NIRCam image, the white dwarf appears on the lower left of the bright central star. This is a planetary nebula. So when a star that's about 8 times the size of our sun and smaller, so that would include our sun, those are too small to go supernova. And what happens is after they've done burning out their hydrogen and helium, and they turn to other elements, the gravity starts to decrease and the shell expands. And the final product of a star like ours is a white dwarf with about half of the original mass that's no longer burning, but is going to take 1 trillion years to cool off. And then it throws off this outside shell, which hangs around for about 20 or 30,000 years and then dissipates. So about half of the mass of the star. And that's what we're looking at here. So there's a white dwarf in the middle, and it's not the bright one. In the NIRCam, one of these pieces of light are really a diffraction spike, which comes from the build of the telescope. It's blocking our view. But here, you can see that's the white dwarf. So by going to a different wavelength, we get a better picture of the white dwarf. That's the central. It's brighter, larger, and redder in the mid-infrared. And the white dwarf is cloaked in thick layers of dust, which make it appear larger. But it's radiating and making that dust glow. But the white dwarf is much more. A white dwarf is the size of our sun. A white dwarf formed by a star the size of our sun would be the size of our Earth. So it's very, very compact. It's much more dense than the sun is right now. And that's the white dwarf. So it's a very small, it's like Earth glowing. And so as you can imagine, it's very tiny compared to that other star. This is an interesting group of galaxies, about 290 million light years away. It's Stephan's Quintet. It's a group of 5 galaxies located in the constellation Pegasus, which you can see from the north. The Hubble image is on the left, and the Webb is on the right. This quintet is notable for being the first compact galaxy group ever discovered. It was discovered in 1877 by a French astronomer named Edouard Stephan. It's also a favorite object for more advanced astronomers to try to find. You can find it in a larger telescope. It takes some time, but it's done. But its real claim to fame is that it was featured in that Christmas classic, It's a Wonderful Life. There is a scene where they have Stephan's Quintet shown up there. There's another picture. This is the Webb. This was the Webb's largest mosaic release. I'm not sure if there was one that surpassed it. I meant to check that and I didn't. It contains over 1,000 images stitched together. to get this image. The picture offers astrophysicists new insights on gravitational interactions of galaxies. There's a lot to be learned from studying Stefan's quintet. And although it's a quintet, that leftmost galaxy is much closer to Earth than the others. It resides 40 million light years from Earth instead of the 290 light years that the million light years that the others reside at. So this is a visual quintet, but it's a gravitational quartet. There's only 4 of those galaxies that are gravitationally held together, and the other one just happens to be in the field of view, which happens a lot in astronomy. You can see things that are way far away from each other, and they look like they're next to each other just because of where they lay in space as viewed from Earth. NASA calls a quintet a fantastic library for studying how interacting galaxies trigger star formations in each other and how the gas in these galaxies are being disturbed. Rarely do scientists get a chance to see all of these processes, which are fundamental to all galaxies, and see it in such great detail. Tight groups like this may have been more common in the early universe, when their superheated infalling material may have fueled very energetic black holes called quasars. Even today, the topmost galaxy in this group harbors an active galactic nucleus, a very active, a supermassive black hole, 24 million times the mass of the sun. That's a big boy. It's actively pulling material and puts out light energy equivalent to 40 billion suns. That's quite a furnace. And here's my last image of the night. NASA released this image July 12th of this year to celebrate JWST's 1-year anniversary. So although I said I'm giving you a 20-month update, I probably should have just called it a 12-month update, 13-month update, because we've only had 13 months of data from the Webb scope. But I'll be back next year. This image is of Rho Ophiuchus. It's a cloud complex, the closest star-forming region to Earth. It displays star birth in a way that's never been seen before. And when I look at it, it could pass as an impressionistic painting, the Museum of Modern Art. When I first saw this, I thought this was like an artist's impression. I didn't think it was a real photo. It's just so ethereal, but it's a real image created by the scope. NASA notes that this is a relatively small, quiet stellar nursery, but you'd never know it from the chaotic close-up that the Webb has given us. You see jets bursting from young stars, crisscrossing that image, impacting the surrounding interstellar gas and lighting up molecular hydrogen, shown in red. Some stars display the telltale shadow of a circumstellar disk, the making of future planetary systems. Right, a circumstellar disk would be like the rings of Saturn, right? That would be a circumplanetary disk. And so we see that some of these stars have a disk of debris around them, which is how you can make planets. So these were just a few of the accomplishments for the Webb telescope in just the first year of operation. A quick look at the European Space Agency's website, their press releases, will show you many, many more accomplishments, including the discovery of water vapor in a rocky planet-forming zone around a star, carbon-rich dust grains in the first billion years of cosmic time, a water vapor plume jetting out of one of Saturn's moons, images of a rarely seen prelude to a supernova known as a Wolf-Rayet star, and many, many more things. So this Webb scope really holds a lot of promise for the future. It's already turning out a lot of scientific papers, and I really look forward to what we're going to see in the next year. And I'll get back to you. For those who don't want to watch it on the web, I'll get back to you and give you a report in a year. So thanks a lot for your attention. I appreciate it.
All right. Thank you, Walt. Thank you all for joining us. So we will be doing a question and answer session. But first, the safety briefing for those of you who snuck in the middle of the presentation. Yes, you still need to hear it. When we go to leave, because it is quite dark, we are using our headlights because I don't want to get run over. I'm sure you feel the same way. That being said, if we have any flashlights, because it is dark and some people might have trouble getting around in the dark, do keep them pointed towards the ground so we don't accidentally blind people. If you need to use the restroom, that is the porta potty to my left in the back there. It would be to your right because that's how directions work. We do have a museum and gift shop area, which I'll be manning after the question and answer session. And with that, how this question and answer session is going to work is I've been staring at a screen, so I'm slightly night blind. Think of me like a T-Rex. If your hand's not up in the air and moving, I can't see you. You're just amorphous people blobs. It's not great, but you know, that's why we don't stare at our screens usually. So, I'm going to start this off by our first online question. Wasn't it the James Webb Space Telescope that found the question mark in the far reaches out there? And have they figured out what is going on with it or what it is?
They have. They did find a question mark out there. It really looks like a question mark. And as far as I know, it's still a question mark.
They have a quest out there for us or something? Like in the video games? The person you need to talk to has a little...
There were theories. I read something about just a couple of weeks ago, and I forgot what the hypothesis was about that. It looked pretty cool. I remember seeing the image, and it was wild how close to a question mark it was.
Right. So like I said, night blind, so is there a question out here? Kind of raise your hand, wave it around. Oh,
There's
perfect.
Hi. I was just wondering, how long is it going to take those quintet galaxies to like collide? How many millions of years?
That's a good question. I don't know. It's that's the fun thing about doing a talk when I cover so many objects. It's like you can't be a specialist on all of them. I don't know how long it would take for some of those to collide. You can see already that these two are colliding already, right? They're in the process of joining together. So I guess my answer is it's happening already.
All right, so our next question out here.
I was wondering, what was some of the other criteria that NASA was using in order to figure out where to pinpoint these, where to pinpoint the Webb telescope to find these images? Was it just images that they found from Hubble previously that they thought they could use to find more information, or are they pointing it towards like potential other areas that they don't really have the information for and hoping to find something or anything like that?
There were many sources. I mean, the Hubble and ground-based telescopes were part of it. Also, astronomers put in projects that they wanted, and some got approved and some didn't. So it came from a wide variety. And then there's sometimes they discover things just by pointing. The Hubble, one of the most amazing early pictures of the Hubble was they just pointed it near the Big Dipper at an area that they thought was totally empty, and they found 1,500 galaxies in the size of the sky that would be covered by a period at the end of a sentence held at arm's length. So they just don't know what. And later on, they started pointing it towards the most massive areas of the sky where it's most crowded. And what happened was they started to see what they call gravitational lensing, which was predicted by Einstein. And that's where you have a supermassive object, say it's 5 billion years away, 5 billion light years away, and there's an object 10 billion light years behind it, directly behind it, but because this object is so massive, the light bends around that object and we see it magnified and very distorted. And so we started to see some really wild stuff even in the most populated areas of the galaxy. We expected to see galactic gravitational lensing, but we're seeing an awful lot. We even caught one of a supernova, 4 instances of the same supernova. It's called an Einstein cross, where the light from the supernova bent around a heavy, massive galaxy cluster, and we saw 4 different shots of that supernova at slightly different instances in time.
All right. So our next online question is, are the individual mirror pieces also parabolic, or are they just flat and arranged in the parabolic manner?
They have some curve to them. You have to make a true parabolic mirror. You have to have some curve in them.
All right. Another question from people out here.
There's one in the back.
Oh, hold on. Let me get you the microphone, because chances are if you have that question, someone else online does. You are going to have to raise your hand and kind of wave it about. Oh, okay. Again, slightly blind in the night.
Thanks. Oh, thanks. My question is, I'm fascinated by the colored images, particularly the last Webb image. And what I'm fascinated by is, how do they determine how to colorize it? I understand there's a team that spends their time colorizing these images. And what's the basis for doing that? How do they create these great images? And
Well,
what colors are they based on?
right. Well, and I imagine that some of it for public release are done for aesthetic purposes, but they generally have, when you're looking at images, they generally denote different elements. So red, well, you see red, you're looking at hydrogen. Green is usually oxygen, and so on. So a lot of times what you're seeing is these images are showing you the different elements, and also how hot things are. Blue is, when you see a blue region, you know that there's hot young stars that are being born there. And the way these things, when you see glow here, it's because there's a very powerful star that's lighting it up. It's called an emission nebula. It's even from like 4 or 5 light years away, some of these stars are so powerful that they can light up that whole area of gas cloud in front of them. But oftentimes, each color denotes an element. And when you're looking at the NASA site, a lot of times they will give you the key to that, where they'll tell you which element is which color. But I'm sure a lot of the stuff released for public, there's some aesthetic value in there too, to make it a pretty picture. Amateur astronomers here do the same thing, and working in visible light. You know, they'll use Photoshop to punch up the colors and make it visually pleasing.
All right. Also, this one actually is a great follow-up to that. If those images are infrared, how are we getting visible light style images?
Because the NASA astronomers are colorizing those images. They're taking the data, that's just the raw data, and they're assigning colors to that data. Because yes, our eyes cannot see infrared. So if we could look in the telescope and see the infrared, we would not see it. We'd see nothing. So yeah, it is colorized. It's like a Ted Turner. They're pulling a Ted Turner on the universe. At least 1 or 2 understood that one.
Yeah, I was like,
my
I don't
my
get
cultural
it.
remarks are, the older I get, the less people understand them. So I can live with that.
All right. Another. Oh, here's a fun comment about the light traveling 13 billion years. At least they're traveling without kids. There's no, are we there yet?
That's pretty funny. I almost put that "Are we there yet?" in there, and I said no. I'm not gonna.
All right. Another question from here. Like I
Fine.
said, handed it. Oh, he has his phone light up. That's
Nice.
actually super useful.
Thank you for the nice presentation. So I also have a question regarding this image showing right on the screen. So I noticed a lot of those image Webb presents, the highest light seems to always have like the beam of the ray, right? And also symmetry. So my question would be, are those coming from the star, nature of the star, or are they coming from how we made the Webb, like its lens, or it's like how we process the images, like the algorithms, whatever? Why it's like the 6 rays there?
Right. Well,
For them.
and
Yeah.
that's now the classic 6-pointed diffraction spike of the Webb, and you're very observant there. Certainly, the light is powering it, right? The brighter the star, the bigger the diffraction spikes. But the way that the Webb and the Hubble are designed, light comes in and hits the primary mirror. right? The primary mirror is a parabolic mirror. So the light hits the mirror and it's focused, and it goes to there we go. Okay. So the light hits this, and then it gets bounced into a secondary mirror. This right here is a secondary mirror, and the concentrated light now goes through here and into the instruments for processing. You can see these holding the secondary mirror, and the Hubble has the same thing. It's got these, and these cause diffraction spikes in the images. So when you have a bright star, those spikes are caused by the way that the telescope is made. Great observation.
They're also doing this in order where it's great follow-up question. Is there a way to correct the image so you don't see the hexagonal lens flare or diffraction spikes?
Yeah, you could Photoshop it, right? And so if you're doing something for aesthetic purposes, if you want to do that, some people like those diffraction spikes. The thing is, it's not scientific to use Photoshop to guess what was behind that white line, because you really don't know. You can copy, right? The way Photoshop works is you can copy a dark spot here and cover up the line, but you're not being scientific about it because you don't know what's there unless you have a mosaic. If you have a mosaic, then you could do that better.
Sorry, I keep trying to keep the toads out of the museum area. Oh, no live specimens in the museum area. Hey, at least it was a couple chuckles. Was there another question out here? Oh, perfect. Keep your hand. Oh, hold on, I didn't hear you.
The question was, can we use the telescopes tonight? And
Yep.
you know, we actually will be using the telescopes tonight because, as I said, this is one of the most beautiful nights I've seen in a whole bunch of time. So those sheds we have, we roll off the roofs, and there's telescopes in there. And if the roof is rolled off a shed, just feel free to go up to the door. Sometimes there's a line, and sometimes there's folks observing right on the lawn with their own scopes. Don't be shy. This is public night. We do this for the public, and we want to show you a bunch of stuff, and there's some really cool stuff. You might see the Ring Nebula. Not the one I showed you. That's in the southern hemisphere. But there's a Ring Nebula that's right over our heads. Hercules cluster. There's all kinds of cool stuff out there. So, yeah, just walk up and take a look.
Yeah, most of our volunteers have a name tag. I am horrible at remembering to actually wear mine, so I'm setting a very poor example. But always feel free to find one of our observer volunteers, and they'll be more than happy to answer those questions. You know, ask them, hey, what are we looking at right now? If you happen to know if there's a certain object you're looking at, a lot of them will also then focus on those.
And just a quick tip for those new. There's a bunch of astronomy guides apps. One simple one to use is called Sky Guide, and it's free. And once you get it, if you press the compass on the upper right hand corner, you can just point it at the sky, and it'll show you. Like right now, mine's showing me Saturn is right there. And so if you wonder what it is, if you download this app Sky Guide, you just point it around the sky, and I can see the Milky Ways right here, Sagittarius. So it's a really cool little thing to do, and you can put it in night mode, so it's in deep red instead of, you know, ruining your eyesight. Deep red does not affect your night vision, and that's why we use as much. That's why we use red filters on telescopes. That's why astronomy programs can come with a night mode, which is red. So
and that's also why things like the porta potty and any lights we have in the observatories, in the roll-off sheds, are colored red as best we can, just to help give a little light enough to see by, but not enough to try and wreck your night vision. All right, so I did notice we are starting to come to the end of our online questions, so I am going to ask the online people, if you have a question, do get those in. They generally hear me a minute or so after I say something, because that's how live streaming stream delay works. With that, was there another question here? Like I said, raise your hand. And was that a raising your hand or getting resituated. Right. So our next online question: if our solar system is still around and going strong when Andromeda joins us, is there a chance our solar system would get additional stars, planets, objects?
Yeah, it'll be combined. No, not our solar system. It'll be combined. By that time, 4.5 billion years from now, the sun is going to be so big that we will be inside it. So it's really not something that we even need to think about. But there'll be more stars. There'll be new stars formed. But I don't think it would be very rare for us to get another chunk of rock circling the sun.
Right. Another question from out here. Perfect. Hey, Chris, can you kick the toads out of the museum? He's listening, so.
I just have a follow-up to that. If two galaxies collide,
Mhm.
do they pull off of each other on the edges? Like, gravitational pull, does one star become more dominant and start taking from the other? Is that a silly question?
No, it's not a silly question. It's a very complex dance that they do. Their gravity, they compress dust clouds and form new stars, and they reconfigure. And of course, most galaxies have black holes. So you have two black holes. We have seen pairs of black holes orbiting each other, which is a very powerful thing. And of course, the black holes will eat any matter that comes near them. It's called the accretion disk. So yeah, all kinds of strange things do happen, but there's so much space between stars. The closest star to us is 4 light years away. That when they come together, it's not as catastrophic as you think, but still, there's a lot going on there.
All right. I know there were a couple more hands that went up, but I lost you because you put them down. Were there more questions out here in the pub? Right. So our last online question is actually, isn't there an oldest tree named Methuselah? And why that name for the presumed oldest things?
Because in the Bible, there is a character called Methuselah who was the oldest person who ever lived, over 900 years old. And so anything named Methuselah presumably is named after this Old Testament figure, Methuselah.
Right.
And I won't be angry if you leave to look at stars.
Yeah, they
it
are
is a beautiful
actually
night.
looking quite wonderful, which is a great change from what we have been mostly experiencing since April. Any last minute questions here? If not, thank you all for joining us. Thank you. Both our people here and our people online. Thank you, Walt, for another great presentation. Like we said, the observatories we do have several telescopes open, so do feel free to ask our volunteers what's up in the night sky.
Yeah, have a great night. It's going to be good observing. Don't be shy.